Good morning, everyone. Myself Piyush Sunhare, and my topic is thrashing in the operating system. Now, in introduction to thrashing, what is thrashing? Thrashing occurs when a computer's virtual memory system is overstressed, leading to excessive paging and a significant drop in performance due to frequent context switches. What are the causes of thrashing? Thrashing can be caused by insufficient physical memory, a higher number of active processes, or applications that require more memory than is available, resulting in constant paging. When was thrashing first identified? Thrashing was first identified in 1960s with the advent of virtual memory systems, notably observed in early multiprogramming environments, which struggled with resource allocation. What are the early solutions to thrashing? Early solutions included increasing physical memory, optimizing existing processes, and implementing page replacement algorithms to better manage memory usage and reduce unnecessary paging. Mechanisms of thrashing. First, the role of paging. Paging is a memory management scheme that eliminates the need for contiguous allocation of physical memory, allowing processes to be divided into fixed size blocks or pages, improving flexibility and efficiency. Impact of page faults. Page faults occur when a program accesses a block of memory not currently mapped to physical memory, leading to delays as the operating system must load the necessary page from disk, resulting in performance degradation. Memory hierarchy. Cache memory. Cache memory is a small, high-speed storage layer that temporarily holds frequently accessed data to speed up retrieval times, enhancing overall system performance and reducing memory latency. Swap space. Swap space is a portion of the hard drive designed to use as virtual memory, enabling the system to offload inactive pages from RAM, although relying on it can result in increased thrashing if accessed excessively. Impact of thrashing: performance degradation, CPU utilization. High levels of thrashing can lead to significantly reduced CPU utilization as the processor spends more time managing memory rather than executing processes, causing inefficiency. System response time. Thrashing increases system response time by introducing delays in process execution, making applications slower to respond to user inputs and reducing overall user satisfaction. Resource utilization. Disk input-output activity. When thrashing occurs, disk input-output activity escalates as the system continuously reads from and write to the disk, leading to increased latency and potential bottlenecks in data processing. Impact on other applications. Thrashing can adversely affect other applications by consuming excessive resources, causing them to slow down or even halt, as system resources are monopolized by thrashing processes. Network traffic. Increased thrashing can lead to higher network traffic due to frequent communications between processes and external resources, impacting the overall network performance and increasing latency. Detection of thrashing. Monitoring system performance. First, performance metrics. Performance metrics are specific measurements that quantify system performance, such as CPU usage, memory utilization, and I/O operations, crucial for identifying thrashing scenarios. Next, diagnostic tools. Diagnostic tools are software applications that help monitor system performance in real time, allowing administrators to assess resource utilization and pinpoint potential problems linked to thrashing. Analyzing page fault rates. First, page fault frequency. Page fault frequency measures how often page faults occur during a specific time frame, serving as a vital indicator of whether the system is thrashing excessively. Second, threshold values. Threshold values establish acceptable limits for page fault rate, assisting system administrators in determining when intervention is necessary to prevent performance degradation from thrashing. Solutions to thrashing. Definition of working set. The working set refers to the set of pages that a process is actively using during a specific time interval, allowing efficient management of memory resources and reducing page faults. Adjusting working set size. Adjusting the size of the working set is crucial for balancing memory usage. Too large can lead to thrashing, while too small may cause excessive page faults, impacting system performance. Page replacement algorithms. First, least recently used, also known as LRU. LRU is an algorithm that replaces the page that has not been used for the longest period, effectively predicting which pages are least likely to be needed again soon. Second, first in first out or LIFO and optimal page replacement. The FIFO algorithm removes the oldest page in memory when a new page needs to be loaded, while the optimal algorithm replaces the page that will not be used for the longest period, theoretically providing the best performance. Load control. First, process prioritization. Process prioritization involves assigning different importance level to processes, ensuring that critical processes receive more resources, thus minimizing thrashing in resource-constrained environments. Second, reducing multiprogramming level. By limiting the number of concurrent processes running in the system, reducing the multiprogramming level can lessen competition for resources, decreasing the likelihood of thrashing. Third, admission controls. Admission controls manage the entry of processes into the system by evaluating resource availability, allowing only those processes that can be executed without causing resource contention to enter. Preventive measures. Memory management policies. First, proper allocation of resources, ensuring resources like CPU, memory, and storage are allocated correctly to avoid bottlenecks and improve system performance and stability. Use of priority scheduling. Implementing scheduling algorithms that prioritize tasks based on urgency or importance helps manage workload efficiently and prevents resource starvation. System configuration, hardware upgrades, regularly updating hardware components such as RAM, solid state drive also known as SSDs, and GPUs enhance system performance, increases capacity, and prepares for more demanding applications. System tuning, fine-tuning system settings and configurations can optimize performance, improve speed, and enhance responsiveness by aligning system capabilities with workload demands. Software optimization, optimizing applications, refining application code and architecture leads to faster execution times, reduced memory footprints, and overall improved user experience and resource utilization. Using efficient algorithms, employing algorithms that maximize speed and efficiency can significantly enhance application performance and reduce the computational resource required for tasks. Case studies and real-world examples. Case study 1. Thrashing in a multi-user environment. In a busy multi-user system, excessive page swapping occurred due to high user concurrency, leading to degraded performance and user frustration, highlighting the need for efficient resource management. To address the thrashing, a combination of increased physical memory and optimized scheduling algorithms was implemented, resulting in improved response times and user satisfaction. Case Study 2. Thrashing in Cloud Services. Scenario Description: a cloud service provider experienced resource contention as multiple applications shared limited virtual memory, causing significant latency and affecting service level agreements negatively. Solutions implemented: the implementation of auto-scaling policies and resource isolation techniques helped mitigate thrashing, ensuring that each application could operate within its own defined memory limits, thereby enhancing overall service performance. Analysis of successful implementations. The long-term impact. Successful implementations lead to sustained improvements in system performance and reliability, providing a scalable framework that adapted to changing user demands over time. Best practices. Key best practices include monitoring resource usage closely, designing systems for scalability, and establishing clear user policies to minimize contention in shared environments. Now, in conclusion to thrashing, first key point: the importance of understanding thrashing and its impact on system performance, with emphasis on efficient resource management and allocation. Key point 2: highlighting various strategies and techniques for preventing thrashing, including workload balancing and effective memory usage. Key point 3: discussion of case studies that illustrate successful thrashing preventive measures, reinforcing the effectiveness of proposed solutions. Future directions in thrashing prevention. Emerging technologies. Explanation of how advancements in artificial intelligence and machine learning can optimize resource allocation and reduce thrashing occurrences. Research opportunities. Identifying gaps in current research and suggesting future studies to develop more robust thrashing prevention methods and policies. Policy implications. Understanding the role of organizational policies in establishing best practices for resource management to mitigate the effects of thrashing. Final thoughts on the topic: Recap of importance, reiterating the critical nature of addressing thrashing in computer systems to ensure optimal performance and user satisfaction. Call to action, encouraging stakeholders to implement discussed strategies and remain vigilant for potential emerging trends in resource management. Vision for the future, a hopeful outlook for the future of computing environments where thrashing is effectively managed through innovation and thoughtful practice.